Bode plot. So Bode plots are also called logarithmic plots. It has two parts. One is the algorithm of magnitude of a sinusoidal transfer function g of j omega into h of j omega expressed in dB versus frequency. And the second one is phase angle in degrees versus frequency, both plotted on the log scale. So first we draw the approximate plot using straight line asymptotes, and then we do some corrections on the approximated plot to obtain accurate plot. So since logarithm scale is nonlinear, we cannot locate the point at omega equal to 0. On the log scale, since log 0 is equal to minus infinity. So generally, frequency ratios are expressed in terms of decades, that is on x-axis. To express the magnitude of g of j omega and h of j omega in dB, we shall take 20 log of magnitude of g of j omega and h of j omega. So to draw the complete Bode diagram or Bode plot, we have few basic factors in the function transfer function. So first one is gain k, second one is pole at the origin, third one is multiple poles at the origin, fourth one is 0 at the origin, fifth one is multiple zeros at the origin, sixth one is factor of the form k by j omega all to the power of r, seventh one first order pole on the real axis 1 by 1 plus j omega t, multiple poles on the real axis 1 by 1 plus j omega t all to the power of n. Ninth one, first order 0 on the real axis 1 plus j omega t, multiple zeros on the real axis 1 plus j omega t, and 11th one, quadratic poles, 12th one, quadratic zeros. So these are the basic factors used to draw the Bode plot. So let us look at our Bode diagrams. Let me share the whiteboard. So we had run Bode plot for constant gain k, where you have positive dB when k greater than 1, negative dB when k less than 1, and at k equal to 1 it is 0 dB line. And the phase angle plot is also 0 degrees. Second one, it is pole at the origin. I have a straight line with a slope of minus 20 dB per decade, and the phase angle is minus 90 degrees. Later we draw the Bode plot for multiple poles at the origin, and again the straight line, the magnitude line is minus 20 n dB per decade. Phase angle is minus 90 degrees into n. And third one we completed. Let us take the fourth one. So the fourth one is pole at the 0 at the origin. So let me clear this board. Yeah. So let us draw fourth one. That is 0 at the origin. So what is the log magnitude of j omega in dB? The log magnitude of 0 at the origin is 20 log magnitude of j omega. So what's the value? It is 20 log omega in dB. So this is the magnitude of the 0 at the origin. So again, to draw or to find the straight line of this 0 at the origin, let us take omega equal to 0.1, omega equal to 1, omega equal to 10. Now what is the corresponding magnitude when omega equal to 0.1? That is 20 log 0.1. So what's the value? So it is 0.1, it is 1 by 10, 10 to the power of minus 1, it is minus 20 dB. I think you know the logarithmic values. Next one, when omega equal to 1. So when omega equal to 1, it is 20 log 1. And we know this value when when omega equal to 1, it is 0 dB line. Third one, it is 20 log 10, which is plus 20 dB. Now look at all these magnitudes. When omega equal to 0.1, it is minus 20 dB. Magnitude is minus 20 dB. So when you multiply with 10, that is your frequency is taken as decades. That is multiplied by 10. And you have a change in magnitude. It was dropped from minus 20 dB to 0 dB. Or you can say there is a 20 dB increment in the magnitude. So similarly, from this 0 dB to 20 dB, there is a 20 dB increase. So I can say it is a plus 20 dB per decade straight line. This is the conclusion. So what's the magnitude graph? It is a plus 20 dB per decade straight line. So let us look at that board diagram for this magnitude. Let us draw the graph, assume, and we should draw both magnitude plot and phase plot in the same graph. So that's why I should take 2 axis log omega. So it is magnitude in dB, right? This is the 0 dB line. Assume this is a 0 dB line. So I can say this is 20 plus 20 plus 40. Here it is minus 20 minus 40. And here I can say pi in degrees. I assume this is a 0 degree line. And it would be plus 90 degrees. It would be minus 90. So you can even take 45 degrees or 25 degrees length. It depends on your problem. If you are getting less angles, that is 30 degrees, 40 degrees, you can take one scale or one unit is equal to some 30 degrees, 45 degrees, something like that. So let us draw the magnitude plot of j omega. So when omega equal to 0.1, let me denote 0.1 here and 1 here, and this is 10. So what's the value? Omega value 0.1, it is minus 20 dB. So I use another color for this. So I have a point here. This is 20 dB minus 20 dB. And when omega equal to 1, it is 0 dB. When omega equal to 10, it is plus 20 dB. See? And this is a straight line. So assume this is a straight line connecting all these points. So what is that? It is a plus 20 dB per decade. Right. So what about phase angle? So obviously it is a plus 90 degrees. This is magnitude plot and this is phase angle plot. Okay. This is about 0 at the origin. So it's a straight line with slope of plus 20 dB per decade and phase angle is equal to plus 90 degrees. So let us move on to the next basic factor, multiple zeros at the origin. Fifth one, multiple zeros at the origin, which is j omega whole to the power of n. So what's the log magnitude for this j omega whole to the power of n? It will be 20 log modulus of j omega whole to the power of n. What is this value? M equal to 20 n log omega. Okay. So again, we do the same for this. That is when omega equal to 0.1, what is the magnitude? When omega equal to 1, the magnitude. When omega equal to 10. So it's a value. So when omega equal to 0.1, your magnitude will be minus 20n log 0.1, which is equal to, so minus 20n dB, and then 20n log 1 is 0 dB again, and then 20n log 10, which is 20 into n dB. Again, if you look at this magnitude values, there is an increment in 20 into n dB per decade. So this is the magnitude plot for j omega whole to the power of n. So let us draw this. So first draw the magnitude plot with log of omega, magnitude in dB. Assume this is a 0 dB line, that is 20 and 40 minus 20. I hope that's enough, minus 40. And then you draw the one more x-axis. This is pi phase angle in degrees. Assume this is a 0 degree line and it is a plus 90, so minus 90. So let us put the points on the graph. So when omega equal to 0.1, let me draw the points 0.1, 1 here, and 10. So when omega equal to 0.1, it is minus 20 into n. So let us change the value, this value as 20n, 40n, minus 20n, minus 40n. Right. So let us put the point here, J, and then it is 0 dB, and then plus 20n. So again, it is a straight line. Assume this is a straight line, sorry. I got some. Yeah. Now this is plus 20 into n dB per decade. So similarly here also we'll add n here. Let it be plus 90n and minus 90n. Our Bode plot will be, assume this is straight line. So it is plus 90n. So the phase angle is plus 90. Yeah. So this is your magnitude plot. This is your phase plot. Right. So this is about basic factor of the type j omega whole to the power of n. So what's the additional point here? You have only n in place of 20. So we replace 20 dB by 20n and phase angle by, or phase angle or magnitude are multiplied by n. Similarly in the case of poles. So this is another basic factor, Bode plot. So let us move on to the next Bode plot, sixth one. Factor of the form k by j omega all to the power of r. You frequently find this factor, some gain by j omega all to the power of r. So how do you find the Bode plot of the form k by j omega all to the power of r? Again, let us proceed the finding the magnitude of this form. So what is the magnitude? It is 20 log magnitude of k by j omega whole to the power of r. So what is that? It will be minus 20 into r log omega plus 20 log k. Just use logarithmic summation minus 20 into r log omega plus 20 log k. This is your magnitude. Let us go when omega equal to 0.1. What's the value? Omega equal to 1 and omega equal to 10. Right? So when omega equal to 0.1, what's the value? Minus 20r log 0.1 plus 20 log k, which is equal to, it is 0.1 again. So it will be plus 20r. Sorry. Plus 20r plus 20 log k. So next, when omega equal to 1, it is minus 20r log 1 plus 20 log k. So again, this is 0, this one is 0. So we have only 20 log k. So both are in dB. So coming to this, when omega equal to 10, it is minus 20r into log 10 plus 20 log k. So what's the value? It is minus 20 r plus 20 log k. Both are in dB. So when we are changing the frequency in terms of decades, there is a change in the magnitude. Let us find out the difference in magnitude. What's the difference between first two quantities? Let's subtract them. You have minus 20 into r dB difference. What's the difference? It is if there is a change in the frequency in terms of tens, you have a minus 20. Let me write here this side is minus 20 r dB. Even if you look at the second one, the difference is minus 20 r dB per decade. Isn't it? Since 20 log k is constant, so assume this is 0, you can easily find out the difference. So this would be plus 22, 0 and 0 to minus 20. So that's how you can easily find the difference among the values. So let us draw the Bode plot for this. But what about the line which is, this line is touching 0 dB, right? So any line, straight line will touch the 0 dB line. So where it touches, so let us find out the value where your straight line is touching the 0 dB line. That is, you can write it as it has 0 dB when your 20 log k by j omega whole to the power of r magnitude must be equal to 0. So I can write it as minus 20r log omega plus 20 log k must be equal to 0. Right. So if you do some simple mathematics, you will get omega equal to k whole to the power of 1 by r. So where it touches, your straight line will touch the 0 dB line when omega equal to k whole to the power of 1 by r. So let us draw this Bode plot. Log omega, and also log omega, Bode plot, magnitude in dB. Again, this is 0 dB line. So what about the values? Again, it's a minus 20 into r dB per decade. So your straight line will be always tending towards like this, right? I can say. So here this point is nothing but when omega equal to k by whole to the power of, sorry, this is I can directly write it is so this is the point where you are touching the 0 dB line now. So when omega equal to 1, what's the value? When omega equal to 1, it is 20 log k, right? So I can say this is your 1, or it depends on your k and r values. Assume this is here, and you have some 20 log k value. So this bit will be your 20 log k. I can say this. Okay, so this is your line with minus 20 into r dB per decade. So what's the difference between all other basic factors, and with this we should find out the magnitude value and omega equal to some k to the power of 1 by r. So we need to find out this point and this value, and later you place all your points and you will get Bode plot. Similarly, for this it is pi in degrees. So let it be 0 degrees, and we know the value since it is 20r minus 20r dB per decade line. Can say your phase plot will be this. Assume this is straight line. Okay. So this is your magnitude plot and this is your phase plot. So if you have any questions, you can ask till this point. Any questions? So if you don't have any questions, let us move on to the next basic factor. One by one plus j omega t. Seventh one, the basic factor of the form 1 by 1 plus j omega t. So mostly you will get a basic factor of the type k by j omega whole to the power of 4 and this type of basic factors 1 by 1 plus j omega t. But if you understand these two factors, it's very easy to draw the Bode plot. Of course, first 5 are fundamentals to draw the Bode plots. So they are also needed for drawing the Bode plot, but these two are very important. So let us find out the magnitude of this factor. So what's the magnitude? Magnitude would be 20 log magnitude of 1 by 1 plus j omega t. So I can write it as 20 log 1 by root over 1 plus omega square t square, or it would be 20 log 1 plus omega square t square of minus of, and this would be minus 10 log 1 plus omega square t square, right? So here we have one interesting point of this magnitude. We have some parameter called time constant t. So this is your time constant t. So because of this parameter, we should do some more analysis on this magnitude plot. So let us find the magnitude for low frequencies. So low frequencies means your omega, your frequency much less than 1 by t. Since it depends on your time constant value, so let us take omega is much less than 1 by t. So what's the value? When omega is much less than 1, there is low frequencies, your magnitude would be minus 10 log 1. So why it is minus 10 log 1? So which is first let us find out the minus 10 log value, which is 0 dB. Since our 1 plus omega square t square would be 1. Since your omega value is very small, so we can neglect this term, and this would be 1 plus small value is equal to 1. So I can replace 1 plus omega square t square by 1. I can say approximately. So this is 0 dB. So for lower frequencies, this particular basic factor has 0 dB line. So let us find out the magnitude curve for higher frequencies. So here I can write a conclusion. The log magnitude curve, the log magnitude curve at low frequencies is a constant 0 dB line. For low frequencies. So let us find out the magnitude for higher frequencies. So I'll write here for higher frequencies. That is omega is much greater than 1 by t. Your magnitude value would be minus 10 log omega square t square. So this is equal to minus 20 log omega into t. So why it is omega square t square? Again, 1 plus omega square t square is approximately, since your omega value is large, much larger value, and this would be approximately equal to omega square t square. So it would be minus 20 log omega t, or I can write it as it is minus 20 log omega minus 20 log t, right? So can you recall this type of basic vector, minus 20 log omega minus 20 log k generated? So then we can definitely say this one is a decaying magnitude. So that would be minus 20 dB per decade. So I can say this is minus 20 dB per decade, and so of course some subtraction is there. So I can say one more point here. The log magnitude versus log frequency curve of 1 by 1 plus j omega t can be approximated by two straight line asymptotes. One is a straight line at 0 dB for lower frequencies, and other one is again a straight line with a slope of minus 20 dB per decade. Now what about the frequency at omega equal to 1 by t, right? What about the frequency when omega equal to 1 by t. So this frequency is called break frequency or corner frequency. This is called break frequency or corner frequency. Why it is called break frequency or corner frequency? Before omega, that is or less than values or lower frequencies, you have a one straight line, that is 0 dB line. After omega, you have another straight line with minus 20 dB per decade. So see this basic factor, and we assume that your low frequencies and higher frequencies. We made some assumption, right? So that's why you will get some error in this Bode plot. So we should make some correction after drawing the approximated plot. So here we'll get approximation. So I can write it as here the conclusion points. So it has two straight line asymptotes. One is 0 dB line for 0 less than omega less than 1 by t. Another one is, I'll write it another one. Minus 20 dB per decade asymptote. That is for 1 by t less than omega less than infinity. Right? So when omega equal to 1 by t, this is called break frequency. So these are the 3 points in this. When omega equal to 1 by t, it is called corner frequency. And for this range, it's a 0 dB line. And for this range, it is a minus 20 dB per decade line. Right? So let us find out the error introduced in this basic factor. Since we made some approximation, we have some error in this magnitude. So I'll write it here. The error in log magnitude curve of 1 by 1 plus j omega t for 0 less than omega less than or equal to 1 by t is given by, how do you find original value minus approximated value? So what's the original value? Original magnitude is minus 10 log of 1 plus omega square t square. So this is your original magnitude of 1 by 1 plus j omega t, isn't it? So what's the approximated one of the for this range, that is omega much less than 1 by t, low frequencies, the magnitude is minus log 1, isn't it? So this is your error in the magnitude plot. So therefore, first I'll find the error at the corner frequency. The error at, so this is your error. You can say this is your error. So I want to find again this error depending on your t value, omega value, right? So the error at the corner frequency, first let us find out the error at the corner frequency. That is when omega equal to 1 by t. Yes. So when omega equal to 1 by t, it would be, my error would be minus 10 log 1 plus 1 minus, so minus, sorry, this is 10 log 1, no? Minus 10 log 1. So this would be plus 10 log 1. So what's the value? This would be, can you calculate someone? Can someone calculate this value? This log 2 is 10. Can someone tell the value? Minus 10 log of 2 plus 10 log 1. Or can I call someone? Chakravarti, can you calculate the value? Or someone calculate the value? Rishita? Teja, Harini, Deepika.
Minus 3.01, sir.
Very good. Minus minus 3.01 or 3. So anyway, it is approximately, I can say, it is minus 3 dB. Minus 3 dB. So the error at the corner frequency is minus 3 dB. Suppose you have some value 45 or 35, just draw the line less than this value. That is, you can draw the line at 42 dB or 32 dB. So this is the error. So this is how you can find the error for all values of omega, but we cannot find the errors for all values of frequency. So let us find out one more error. Yet the frequency at which omega equal to 1 by 2t. Let us find out the error. One more error. The error that of the corner frequency. Right. That is at omega equal to 1 by 2t. So again, your error would be minus 10 log 1 plus, what's the value at omega equal to 1 by 2t? It will be 1 by 4 plus 10 log 1. So can you calculate this value? Minus 10 log of 1 plus 1 by 4 plus 10 log 1
minus 0.96, sir.
very good, or approximately minus 0.96 or 7 dB. So I can make it as minus 1 dB, right? So let us look at these values. When omega equal to 1 by t, that is at corner frequency, you have minus 3 dB error, and when omega equal to half of the frequency, you have minus 1 dB error. So to understand this, let us take the values from 0 to, let us say, 100 radians per second, right? Where this 100 radians per second would be the corner frequency, right? Of course, let us take, this is the frequency range of your Bode plot. So here some corner frequency 50 radians per second, right? So at 50 radians per second, you have 3 dB. So let this would be your corner frequency, right? And half of the frequency, that is at omega equal to 25 radians per second, it would be 1 dB. So that's why we took half the corner frequency, right? So we continue this class